UTF-8 is one of the most common and widely used systems for encoding text on computers. There's a very good chance that the webpage you're viewing this video on was encoded using UTF-8. UTF-8 has a number of very interesting and cleverly designed features, but to really appreciate them, I think it's important to understand a bit about the history behind text encoding on computers. When the first ever digital computers were created in the 1940s, the progress was mostly driven by the military. The primary motivation was speeding up the large-scale numeric calculations required for things like projected artillery trajectory tables. As a result, it probably wouldn't surprise you to learn that the storage these computers had could only store numbers, and the only operations they could perform were numeric operations, essentially just simple arithmetic. But as the war ended and computing technology began to advance, programmers began to explore other use cases beyond just numeric calculation. And one of the earliest and most impactful uses of the computer was the storage, manipulation, and output of text for things like word processing, government record keeping, and of course, communication. Now, if you don't know much about how computer hardware works under the hood, it's easy to assume that the technology must have grown to allow not just numbers to be stored in memory, but text as well. And the operations the computer could perform must have expanded beyond just arithmetic and into operations that could deal with text directly, right? Well, surprisingly, no. And in fact, even the most advanced modern computers we have still only store and operate on numbers. Which means that the programmers at the time must have figured out some way to build text functionality over the top of this purely numeric foundation. There's a decent chance that if you've been through a public schooling system, at some point you were assigned a task to write a coded message using numbers in place of letters. And the way these codes usually work is you have a unique number that corresponds to each character in the alphabet, which allows you to encode and decode messages. And in simple terms, that's exactly how it's done on computers. If you want to store a message like hello in computer memory, it first needs to be converted to something like 8, 5, 12, 12, 15. Now, if I asked 100 people to assign a number to each character in the English alphabet starting from 1, it's highly likely that all 100 of them would do it exactly the same way, with A as 1 and Z as 26 in order. But English characters aren't the only thing that those early programmers wanted to represent. You've also got all the punctuation. Now, if I asked the same 100 people to assign a number to each character in the alphabet and also to say 20 different punctuation symbols, I guarantee you that there would be a huge number of different arrangements of the punctuation. Some people might put exclamation mark at 27, some people might put period or comma, some people might decide that the digits 0 through 9 should actually come after the letters before the punctuation, and some people might even choose to put the symbols first before the letters. And now imagine that we need to encode not just lowercase letters, but lowercase and uppercase letters separately. And then finally throw in a handful of invisible characters for formatting or printing like horizontal tab, line feed, end of document. By this point, if I ask those 100 people again, I stand a good chance of ending up with 100 different orderings. And unfortunately, that's what ended up happening when the first text encodings were designed in the 1950s. Text encoded on a machine made by one manufacturer often couldn't be decoded on a machine made by a different manufacturer. And so to address this issue, in 1963, the American Standards Association published what is now known as the ASCII standard for encoding text. ASCII uses 7 bits to encode each character, which means it's using what's called a fixed width encoding. And that means that every ASCII character is exactly 7 bits, no more, no less. 7 bits gives you 2 to the power of 7 possible combinations, which is 128 different codes. Enough to encode the English alphabet both in lowercase and uppercase, as well as 32 control codes and the symbols that you typically find on a modern keyboard. And for those of you who are a little bit more familiar with lower-level computing concepts, the idea of a 7-bit encoding might stand out to you as a little bit odd. Most concepts relating to computer memory tend to come in powers of 2, and on modern computers, the smallest addressable unit of memory is a byte, which is 8 bits. But in 1963, there were lots of other factors to consider. Networking was incredibly slow, so being able to transmit 7-bit text 14% faster than 8-bit made an appreciable difference. And on faster but unreliable storage medium like the tape they used at the time, they could use the 8th bit as a parity bit, which is a primitive form of error detection that can pick up when a single bit in the data has been flipped, which at the time actually did happen quite often. And the reason I'm bothering to explain all this to you is the fact that deciding on a 7-bit format for ASCII had enormous unexpected long-term effects, which we'll get to in just a moment. So ASCII is revised a bunch of times and becomes widely adopted as a standard text encoding, which is great for interoperability between computers. But just like in the 40s and 50s, in the following decades, innovation in computer hardware continues and computers start to become more and more widespread. Fast forward to the 1980s, and computers are becoming more and more popular in non-English speaking countries. And now English only has 26 letters in the alphabet, or 52 if you include lower and uppercase. But other languages like Chinese or Japanese have tens of thousands of unique symbols in common usage. And so in order to prevent an explosion of competing and incompatible standards for encoding all these new characters, in the late 1980s, a working group comprised of members from a number of influential companies published a draft of a standard called Unicode. The goal of the Unicode standard was essentially to assign a single unique number known as a code point to every visual character in every human language, so that like ASCII, we could have a universally agreed upon standard. This was obviously a very good idea, but it's paramount to understand that at this point, all they've done is assign a unique number to each character. Even if we have this agreed upon set of code points, we still need to figure out how we're going to encode these numbers as binary. And this is where the real problem starts. Because the tens of thousands of characters laid out by the Unicode standard are way more than ASCII's fixed 7 bits are capable of representing. And so programmers at this point are faced with a conundrum. Either they accept the fact that different countries and languages will use different text encodings that are incompatible with each other, or they develop a new text encoding that uses more than 7 bits, which is capable of representing all the code points defined in the Unicode standard. Now, this might not seem like such a difficult decision on the surface. If we want to support more languages, we're going to need more bits. Simple as that, right? Well, here's the catch. Even if we got all these organizations to agree to adopt a new standard text encoding, there's still an enormous amount of old software that's been built to work with ASCII that would all break if we adopted a new text encoding. To appreciate how this works visually, imagine your word processing software expects each code point to be represented with 1 byte, that is, 8 bits. If we were to change to an encoding that instead used 16 bits or 2 bytes per code point, even if a document only used characters from the ASCII character set, if we encoded the document in a 16-bit format and tried to read it on an older 8-bit word processor, it would still attempt to interpret each byte as a complete individual code point, which would mean we'd end up displaying garbage. And not only that, but all the documents created and stored in ASCII up until that point would be unreadable on new software until they'd been converted into this new format. Which, if you think about it, would also immediately double their size on disk and in memory, as we're now using 2 bytes to store code points instead of 1. We refer to this type of change as backward incompatible. New software is incompatible with old documents, and new documents are incompatible with old software. But even with the downsides, a number of hardware and software manufacturers, of course now most notably Microsoft, considered this to be a worthwhile trade-off and adopted a new 16-bit wide text encoding that was incompatible with ASCII, that they're actually still using to this day in a slightly different form called UTF-16. But the non-backward compatible UTF-16 and its predecessors weren't seen as a viable option in many cases. At this point in history, email was already starting to gain wider adoption, and the Simple Mail Transfer Protocol, usually referred to by its acronym SMTP, specified that the body of emails had to be encoded using ASCII. So a number of organizations, including the International Standards Organization ISO, Apple, IBM, and Xerox, all had initiatives to develop a backward compatible expansion to ASCII. And actually, several of them concurrently managed to all come up with the same amazing idea. Remember how I specifically mentioned that ASCII only uses 7 bits? Well, at this point in history, the majority of computers are what's called byte addressable, which roughly translates to the idea of an 8-bit byte being the smallest unit of information the computer can work with. So even though ASCII is only a 7-bit encoding, it's almost always being stored both on disk and in memory as 1 byte or 8 bits per code point, with the highest bit, the 8th one, just always being set to 0. So that means we can actually use that highest bit without conflicting with the existing ASCII encoding. But of course, going from 7-bit to 8-bit only gets us 128 more possible code points, so that's not really a viable solution. No, the really clever idea is to use that highest bit to indicate that the current code point is actually more than 8 bits wide. Essentially, sneakily exploiting that single unused bit in the encoding to convert ASCII from a fixed width encoding into what's called a variable width encoding. The idea is that we leave all the existing ASCII characters exactly how they are, which in turn guarantees that any text previously encoded as ASCII is completely valid in this new format, as long as we're using a whole byte for each ASCII character. But if this new decoder sees that the highest bit is set to 1, which it never is in ASCII, it should use multiple bytes to encode the next code point, which, for example, with 4 bytes would give us a total of 2 to the 32, which is 4.3 billion possible sequences. Now, this might sound like the perfect solution, but there are a number of hidden problems in the naive approach. If we're going forwards, old ASCII text files and emails will work fine with this new variable width decoder, but if we're going backwards, what happens when we try and read one of these newly encoded files on an old decoder that expects ASCII? Well, imagine in this potential new encoding, I have a Chinese character like this, which I need, say, 3 bytes to encode. I set the highest bit in the first byte to 1 to indicate that it's a multi-byte code point, and then using a combination of the following 7 bits in the first byte and the 2 additional bytes, I encode the Chinese character. Looks good so far. But what happens if we try to decode this, assuming that it's ASCII? The first byte is not valid ASCII. The top bit is set, so a compliant ASCII decoder could choose to filter it out. But take a look at bytes 2 and 3. Our new decoder would know that these are the second and third bytes of a multi-byte code point. But our old ASCII decoder thinks that each code point is 1 byte wide, so it tries to interpret these as ASCII, and because by chance both of them have the highest bit set to 0, it incorrectly interprets these last 2 bytes as open parenthesis and then the asterisk symbol. Now, in this case, we're just going to display a small amount of garbage text in, say, an email. But ASCII also includes a bunch of special code points for specific functions like new lines or the null terminator to indicate the end of a string, and we could get unexpected or dangerous results if those happen to turn up in the extra bytes of a multi-byte code point. And this means that our encoding so far is backward compatible, so the new decoder can work with the old ASCII data, but it's not forward compatible because the old ASCII decoder can't work with the new data. So there's a bit of back and forth about how to solve this issue, and then in 1992, someone at Unix System Laboratories named Dave Prosser comes up with a nice simple solution. We simply make a rule that in any multi-byte sequence, all the bytes have to have the highest bit set to 1, so they could never be confused for valid ASCII characters. This does mean that for multi-byte code points, we lose 1 bit of range per byte, which for a 4-byte sequence now gives us 2 to the 28 possibilities. Still a very respectable 268 million. So this new encoding is starting to look really good, but it has one very major limitation, which is a classic trap with naive variable width encoding. If we go back to ASCII for a minute, there are some very interesting properties that are often overlooked because they're so simple. So all the ASCII code points are the same width, in this modern case 1 byte, and the format of the encoding is that all the characters are placed in sequence one after another, either in memory or on disk. And in computer programming, when we have a sequence of encoded values that are all the same width and are all placed next to each other, the term we use for that is an array. And arrays have some simple but extremely powerful properties. Because all the elements are the same width, you can find the element at a particular index in the array very easily, because finding the element at, say, index 7 is as simple as multiplying the fixed width of the array elements, which in ASCII's case is 1, by the index, which gives us a memory address 7 bytes from the start of the array. I know that might seem obvious, but it's really important to understand that distinction. The ability to look up a character at a particular index hinges on the fact that the elements are the same width. If I now tell you that instead of 1 byte wide, our elements are anywhere between 1 and 4 bytes wide, how would you find the element at index 7? Well, unfortunately, there's only one way, which is iterating through the entire encoded text one element at a time from the beginning, counting up the elements visited until you reach the 7th one. Amusingly, there's actually a strong parallel here with the characteristics of a linked list. Now, you might assume that this is the major limitation that I was referring to, but surprisingly, this actually isn't so much of a big deal. Looking up, say, the 50,000th character in a UTF-8 text file is actually not that common an operation. And even if you wanted to do something like that, you could easily just iterate through the file once and build a table of offsets that you can use to accelerate your lookup. No, the real problem is that the ability to decode the text at all hinges entirely on knowing what the first byte is. Without the first byte, I can't interpret what the second byte actually means. Sure, if the top bit's 0, I know it's a single byte ASCII character, but if the top bit's 1, how do I know whether this is the first byte in a multi-byte sequence, or the second one, or the third one, or the fourth one? Firstly, this limitation means that for files that are entirely multi-byte code points like Chinese, if we lose any of these bytes, we lose the entire file from that point on, because we can now no longer tell if any of the bytes are at the start of a character or in the middle. And you might think, yeah, this is bad, but something like losing bytes is a rare case, right? Surely. Well, that's actually not true, because if we want to start, say, receiving a text stream over the internet and an arbitrary point some of the way through, it's now actually impossible for the computer to unambiguously decode because we don't know if we're at the start of a code point or halfway through. We would refer to this encoding as requiring synchronization, because if you take just part of a body of text encoded this way, the server sending it to you needs to make sure that the first byte you receive is synchronized to the first byte of a code point, which makes implementation way more complicated and error-prone. Luckily, there's always a hero in these kind of stories, and this problem in particular was solved in just a couple hours in a New Jersey diner by none other than Ken Thompson from Bell Labs. And if you haven't read much computing history before, I'll give you a bit of a spoiler. It's always Ken Thompson. I'll link you the story in the description as it was told directly by Rob Pike, but what I'm more interested in going into here are the technical details. What Ken Thompson was trying to achieve is what's known as self-synchronization, which is a property of a variable width encoding, which means that if you drop into an arbitrary point in some encoded data, there's a way to actually figure out where the nearest boundary of an element is without having to decode the entire thing from the very beginning. And to understand this, first we need to define some terminology to help us refer to the different bytes in a multi-byte code point. The first byte in a multi-byte code point is generally referred to as the leading byte, and any subsequent bytes are called continuation bytes. This means that essentially the problem Ken Thompson needed to solve was unambiguously identifying leading bytes, because those are the synchronization points in the encoding. Dave Prosser's design already uniquely identified 1-byte ASCII characters by having the highest bit set to 0. So if we drop in on a random byte and see the top bit set to 0, we're already synchronized because we know this is a single byte ASCII character. So Ken's problem was essentially reduced to fixing ambiguity with multi-byte code points. How can we tell a leading byte apart from a continuation byte? It might sound funny, but he actually did almost exactly the same thing as Dave Prosser. Ken Thompson decided that all leading bytes in multi-byte code points would start with 1-1, and continuation bytes would start with 1-0. So the highest bit tells you whether or not the code point is a single byte ASCII character, and the second highest bit tells you whether it's a leading byte or a continuation byte. And just to make things really clear, let's walk through the process of jumping to halfway through a 50 megabyte file with this encoding and finding a sync point. If we treat the underlying file as an array of bytes, we can use the properties of an array to jump to the halfway point in terms of bytes, which would be around index 26 million. Then we can check if the highest bit of the current byte is 0. If it is, this is an ASCII code point and we're already synced to a boundary. If it isn't, we know that we're somewhere in a multi-byte sequence and we need to check the second highest bit. If bit 7 is also set to 1, we know we have the first byte of a multi-byte sequence and we're synchronized. Otherwise, we can just move to the previous byte in the sequence and do the same thing again. With a properly encoded file, we'll only ever have to seek a maximum of 3 bytes backwards before finding a sync point, because the widest possible code point is 4 bytes. It's these three innovations, the variable width encoding to support more code points, the preservation of full compatibility with ASCII, as well as the self-synchronizing property, that were eventually formalized into the standard we now call UTF-8, which is the de facto text encoding of browsers and the internet, with more than 99.9% of all web pages declaring a UTF-8 encoding. And just for completeness' sake, UTF itself stands for Unicode Transformation Format. Unicode, as I mentioned previously, is the name for the total set of code points we've all agreed to represent on computers, which includes written languages, symbols, and emojis. And Unicode Transformation Format, or UTF, is the specification for how all the code points defined by Unicode are actually encoded in binary on a computer. The 8 in UTF-8, of course, stands for 8-bit as the base size for the smallest code point, in contrast to UTF-16, used primarily by Windows, in which the smallest code points are 16-bit, or even UTF-32, which predictably uses 32 bits for all code points. Now, all three of these UTF encodings are officially supported and defined by the Unicode Consortium, and can each represent all the code points defined in the Unicode standard. They just use different binary representations to achieve that encoding. And before watching this video, you might have thought, well, what's the point of UTF-32? It just seems like a waste to use 4 bytes for every code point when you could be using between 1 and 4 with UTF-8. But now, hopefully you can intuitively feel that UTF-32 would be much simpler and easier to implement as a programmer, because underneath it's just a fixed width array where each element is 32 bits wide. So there's no need for any of that extra machinery to handle variable width code points or synchronization. So the trade-off is simplicity of implementation in exchange for more wasteful memory and storage characteristics. If you really want to think about it in an abstract way, UTF-8 compared to UTF-32 is sort of a form of compression. So now that you understand a bit more of the history and the motivation behind the development of the UTF-8 encoding, let's have a closer look at some of the features of the encoding itself that we haven't discussed just yet. First up, I haven't actually explained how we decide the number of bytes in a multi-byte code point. This chart from Wikipedia is a great visualization if you have a reasonably good handle on binary and hexadecimal, but given that lots of people understandably don't, I'll annotate it to make it a little bit more clear. In a general sense, a byte is a unit of data that can represent 256 possible values. In other words, the numbers 0 through 255. In our decimal number system, the largest value 255 we'd represent with 3 digits, with 5 in the ones column, 5 in the tens column, and 2 in the hundreds column. In binary, or base 2, a byte is represented instead by 8 binary digits, which is actually what the word bit is short for. And so in binary, the decimal number 255 is represented as 8 ones. Instead of powers of 10, each digit in binary is a power of 2. So we've got 1 in the ones column, 1 in the twos column, 1 4, 1 8, 1 16, 1 32, 1 64, and 1 128. If you add all those up together, you get 255. So these are just two ways of representing the same number. Which of course brings us to base 16, or hexadecimal. Just like how each decimal digit can represent 10 values and each binary digit can represent 2 values, each hexadecimal digit can represent 16 values, with the symbols 0 through 9 being used directly and then A through F representing the numbers 10 through 15. And just like binary and decimal, the columns function exactly the same way. We've got F in the ones column, which means 15 ones, and we've got F in the 16s column, which means it represents 15 times 16, which is 240. So 15 added to 240 gives us our total of 255. Now, if you're at all like me, I found hexadecimal very unintuitive and difficult to understand when I first encountered it. So why do we actually use hexadecimal in the first place? Surely if we just wanted to avoid writing numbers in binary, we may as well use decimal, right? It's much easier to understand. Well, it turns out there's actually a really good reason to represent binary data using hexadecimal. If we take just a single hexadecimal digit, we can represent the values 0 through F. The equivalent representation in decimal would be 0 through 15. And the interesting thing is here that we needed 2 decimal digits to represent 0 through 15 instead of just 1 hex digit. But that doesn't mean that one hex digit just cleanly matches up to 2 decimal digits, because with 2 decimal digits we could represent up to 99, which would require more hex digits. The bases are out of sync with each other. But if we look at the binary representation of 0 through 15, you might notice something interesting. Sure, 15 requires 4 digits of binary to represent, but it turns out it's precisely the largest number that you can represent with 4 bits, which means that 1 digit of hexadecimal perfectly lines up with 4 digits of binary. And for the more math-oriented people in the audience, that's because 2 to the power of 4 is 16. 4 digits of base 2 gives you 1 digit of base 16. As a result, you can represent an 8-bit byte using exactly 2 digits of hexadecimal. It's a much more compact notation than binary that still preserves the ability to precisely visualize the boundaries of the byte. So every single 1-byte ASCII character, for example, has an equivalent 2-digit hex representation. To return to the chart, we can see that they've set this up to represent all the possible values of 1 byte. And if we represent 1 byte using 2 hex digits, we can see that the lower or the rightmost hex digit is going left to right in the table, and the upper or leftmost hex digit is going top to bottom. When we convert this to binary, any hex sequence that has 8 or above in the top digit is equivalent to the top bit in the binary sequence being 1. And hence you can see that the entire first half here is the ASCII encoding where the top bit is 0, and the second half is the UTF-8 encoding where the top bit is 1. Remember how Ken Thompson decided that the continuation bytes should start with 1, 0 in binary? That means that this entire range here is used just to represent continuation bytes. And this is a great visualization of the cost of the self-synchronizing nature of UTF-8. A quarter of the byte is used for this machinery. And that means this bottom section here is where we encode the leading byte for the multi-byte code points. And you can see from this chart that if the top hex digit of the leading byte is either C or D, it's a 2-byte code point. If the top digit is E, it's a 3-byte code point. And if the top digit is F, it's a 4-byte code point. And it's important to note here that there are certain specific values like C0 and C1 and all the sequences after F5 that are strictly invalid and can't be decoded as UTF-8. The standard actually specifically recommends that any character with an invalid encoding be replaced with something that you might find quite recognizable, the now infamous Unicode replacement character, which looks a bit like a question mark on a road sign and has the special 3-byte sequence EFBFBD. You've likely seen this character if you've tried to open something like an executable file or an image file using a text editor. So after we've decoded the first byte, we now know how many extra bytes are going to come after. And we know all those extra bytes are going to be encoded as continuation bytes, which all have the 2 highest bits set to 1, 0, and the following 6 bits used to encode the actual code point. But we still have some unanswered questions. How do these continuation bytes actually contribute to the final code point? And why are there so many different ways for the leading byte to indicate a total length of 2 or 3 or 4? Well, it's actually a remarkably elegant and simple system. When we look at how we encode a 2-byte code point in binary, the first 3 bits are guaranteed to be 1, 1, 0. That corresponds to this range here. 3-byte code points start with 1, 1, 1, 0, and that corresponds to this range here. 4-byte code points start with 1, 1, 1, 1, 0. Starting to see a pattern? That's right. For any non-ASCII code point in UTF-8, the number of leading 1s in the binary representation corresponds to how many bytes there are. 2 1s for a 2-byte code point, 3 1s for 3 bytes, 4 1s for 4 bytes. I just love finding little details like this. It feels like finding a secret message the designers have left for you. So we know that the first few bits of every byte in the code point are going to be fixed depending on the length and if it's a leading byte or a continuation byte. Beyond that, the way that UTF-8 works is that you just take all the remaining bits that aren't a part of the encoding itself and put them together into one big binary number, and that number is your Unicode code point. So that means for a 2-byte value, you have 11 bits to work with, which is 2048 code points. 3-byte values have 16 bits to work with, which is 65,536 code points. And 4-byte values have 21 bits to work with, which is about 2.1 million code points. And there's something interesting here you might have noticed. If that binary number that we concatenate from the leftover bits in each byte of the code point directly corresponds to the Unicode code point, isn't it possible to represent some code points in multiple different ways? For example, code point 2047 in binary is just 11 ones, and that should be possible to represent in 2 bytes, 3 bytes, or 4 bytes. This is actually a major problem, because what happens if you want to compare 2 Unicode strings to check if they're equal? Of course, the highest performance way to do it is just to compare the raw byte sequences to each other, but now because there can be different byte sequences that encode the same code point, we actually need to decode both strings as UTF-8 first and then compare the decoded code points. Not to mention that if you're trying to, say, hash 2 files to compare if they're equal, there could be 2 files that contain exactly the same Unicode text that end up producing different hashes. And so to solve this, the UTF-8 standard mandates that only the shortest representation of a code point is actually used. And so you can't represent the ASCII range of 0 to 127 using 2 or more bytes. Any character in the 2-byte range can't be represented as 3 or 4 bytes, and so on. Just to sum all this up, across 4 bytes of UTF-8, we end up having 2 to the 21 possible representable code points, which is very significantly less than the 2 to the 32 that you might expect given that we're using 4 bytes. That being said, the central Unicode standard only actually defines 1.1 million code points, and as of right now, only about 300,000 have actually been allocated in total, which leaves us with a pretty huge amount of headroom. That is, of course, until we encounter an alien species that uses millions of symbols in their language, but I guess by that point we'll probably have bigger problems to worry about. That's it for the technical details of the specification itself. And just to finish up, I thought it'd be nice to give you a feel for how the various characters and symbols are actually allocated across the entire range of the Unicode code points. With a single byte, you can represent all 128 of the standard ASCII characters, which includes lower and uppercase English, the digits 0 through 9, and the symbols you're likely to find on an English keyboard like hash and ampersand. With 2 bytes, we can represent 2,048 code points in total, which covers most of the human languages that use a small alphabet, such as Greek, Cyrillic, Arabic, and Hebrew, as well as some common symbols like copyright and currency symbols like pound, yen, euro, and others. 3 bytes gives us 65,536 code points and is mostly used to represent various East Asian writing systems such as Chinese, Japanese, and Korean. It also contains more advanced mathematical symbols and the Braille alphabet. 4 bytes gives us 2.1 million code points, and this is the home of most of the modern emoji that you see when you open the emoji keyboard on your phone. There's also a little bit of extra magic that happens here. Even though UTF-8 technically only supports a maximum of 4 bytes at present, there's a special 3-byte character called the zero-width joiner, which is used to stick 2 separate code points together. It's Unicode code point 8205, which in hexadecimal is 200D. And the canonical example is usually the family emoji, which instead of being a single 4-byte code point as you would expect, is actually 4 different 4-byte emojis stuck together with 3 zero-width joiners in between. So this emoji is actually 25 bytes, which is pretty massive in the scheme of things. And this group of code points that are combining to render together in a single visual character is typically referred to as a grapheme cluster. And it's theoretically possible to create grapheme clusters of arbitrary sizes into the kilobytes or larger range. So if you're implementing a UTF-8 parser, it might be a good idea to choose an arbitrary cap on the largest grapheme cluster you'll support. Just before we finish up, I want to talk about one last little thing that I think is really cool, which is how the Korean writing system Hangul is allocated across code points in Unicode. If you've never learned about how the Korean writing system works, on the surface it may look similar to Chinese or Japanese with a large number of possible written characters. But surprisingly, it's actually much more similar to English. Each of these characters is referred to as a syllable and is composed of consonants and vowels drawn from a small, simple alphabet and then combined together using various rules. There's actually only 14 core consonants and 10 core vowels, which for a total of 24 is actually less than English's 26. As a result, you might be surprised to learn that Hangul actually occupies 11,184 code points in Unicode. But if we only need 24 for the alphabet, what's the reason? So Korean syllables can have up to 5 or so subparts, which if we were using zero-width joiners to combine into larger syllables would require 27 bytes for a single syllable. And this would make encoding Hangul unacceptably expensive compared to a specialized encoding, and I think it would have been pretty hard to convince the Koreans to actually adopt Unicode in the first place. Given it had already been decided that Hangul would be in the 3-byte range in UTF-8, they had a lot more space to work with, and as a result, they came up with a really clever idea. So the first part is reasonably obvious. There's a unique Unicode code point not just for each consonant and vowel in Hangul, but for each complete syllable as well. So every one of the 11,000 possible combinations is representable with just 3 bytes. You can almost think of it like a cache for those final syllable characters. But there's a little bit of subtlety here. Because Hangul is a real writing system used by real native speakers every day, one of the most common operations is typing Hangul in with a keyboard on a phone or a computer. And just like English keyboards, Korean keyboards have keys mapped to each consonant and vowel, and to type in a syllable, you might, for example, type consonant, vowel, consonant, essentially building up the final syllable from the parts. And of course, if you make a mistake, you can press backspace to delete part of a syllable. Now, if the code points for those final syllable characters were allocated randomly, this process of building up a syllable from consonants and vowels would actually pose a significant computational challenge. You'd essentially have to implement a gigantic set of tables sort of reminiscent of a huge switch statement that encoded every possible sequence of combinations and mapped them to their final code point. And so to make this process easier, the Hangul syllable block actually has some very clever internal rules. There's a simple mathematical formula that you can use to derive the code point of a syllable from the code points of the consonants and vowels that it's comprised of. This syllable here would traditionally be romanized as either KIM or GIM. It's the first syllable in kimchi, as well as the most common Korean surname, Kim. Let's break this down using the formula. We take the first consonant and get its value in the first table and multiply it by 588. Then we take what's called the medial, which is this vowel E, look up its value, multiply it by 28, and add it to our current total. We then add the value of the final consonant from this table, and then finally we add the start of the Unicode Hangul syllables block, which is 44,032. That gives us a total of 44,608, which converted to hexadecimal is AE40. And if you go and look up U plus AE40, you'll find the Unicode character for the entire syllable Kim. Pretty cool, huh? Just as a small aside, a couple of years ago I built a little puzzle game where the main mechanic is splitting and combining Hangul syllables, so if you want to check that out, I'll put a link to it in the description of the video. Of course, Korean isn't the only language with a clever internal implementation. There are lots more secrets hiding in the Unicode standard. I hope this video demystified the topic of Unicode and especially UTF-8 a bit for you. Thanks for watching.